Hi everyone, I'm Toby Kramer, current postdoc at CBE, and today I would like to introduce a new thermal comfort metric called Spatial Thermal Autonomy that you can use in early stages of building design. So for the next 15 minutes, I will talk about spatial thermal autonomy, what it actually means. I will also present a case study that we ran to evaluate the metric. But before I dive into this, I really want to start with some context. Because what I assume is that some of you ask yourself, why do we need a new metric? So in order to answer that question, I really want to recap the conventional workflow and metrics that we use for thermal comfort evaluation. I assume that many of you are familiar with this workflow. We start with a building model. We then separate it into thermal zones. Each of these thermal zones is then simulated separately. And at the end, we have hourly indoor climate data, and we use thermal comfort models like the PMV model or the adaptive model to make an assessment of thermal comfort on an hourly basis. What we do then is to aggregate these results into a single value metric. I think that some of you know metrics like the percentage of time within a certain PMV range, or the number of hours higher than 28 degrees Celsius or 82 degrees Fahrenheit. So this is the conventional approach. What we found is that this has actually quite some problems. First of all, when we look into the thermal zoning, we usually only look into the zone mean, so the center point of that zone. Also, when we run the simulation, especially in early design stages, we often assume that we have an air conditioning system. So we were questioning if this is the best approach for building design, especially in the early design stages. So what we are proposing with a new metric is for these points to provide an update. First of all, running spatial simulations with a much higher granularity, and also, especially in the beginning, avoid using or assuming HVAC or AC systems when we run these simulations. So now I want to continue with what does spatial autonomy actually mean. To make it easier to understand what I'm talking about, I want to introduce two key terms that you might already be familiar with. The first one is spatial thermal variability. Some people call it heterogeneity, but for me as a German, it's quite hard to pronounce, so I usually stick to variability. And what this actually means is that we talk about the spatial variation in thermal conditions across a space. So if you look at the right-hand side of the slide, you see a situation that's pretty typical for many modern buildings where we have a highly glazed facade, the sun is coming in. And what that means is that closer to the window, it can be much warmer than deeper into the room. So that's what we call spatial thermal variability. The second term I want to introduce was introduced by Brandon Levitt and his colleagues in Alameda roughly 10 years ago. And this term is called thermal autonomy. So what thermal autonomy actually means is that we want to optimize the ability of a building to provide thermally comfortable conditions by running it on passive means only. And usually we say, or we name the percentage of time and how this is achieved. So in this case, it would be 61%. What we want to do with spatial thermal autonomy is basically to combine these two aspects. So in the end, we would define spatial thermal autonomy as the percentage of occupied floor area where a thermal zone meets a given thermal comfort criterion. This can be the PMV index or the adaptive model through passive means only. So first element is area. The second one is that we want to look into passive simulation or passive performance only. So what this gives us is that we can now account for spatial variability in a space, and we focus on optimizing passive performance before we introduce an air conditioning system or HVAC systems. So to make it easier for you to understand how this might work in practice, I want to give you a quick run through. So first of all, we have to run a spatial simulation. So instead of looking only into one point, in this case, we will look into 25 different points. So usually it's a regular grid of different nodes, so maybe on a 1 by 1 meter grid. And we have to run this simulation passively to get this kind of data. What we do then is that on an hourly basis, we make an assessment of thermal comfort for each of these points. Again, we can use the PMV model or the adaptive model. And in my example on the right-hand side, a red dot denotes uncomfortably hot conditions, a blue dot denotes uncomfortably cool conditions, and what is displayed as white usually means neutral. So in this case, we have 25 points, and 9 out of these points are neutral. So basically, in this case, and as an hourly result, the STA would be 0.36 or 36%. That means that 36% of the space are likely to perceived comfortable for this point in time. But that's not enough. It's just an hourly result. To guide our design, we usually tend to look into only a single value metric, as I said earlier. So what we need to do is to make a temporal aggregation of these results. To be able to do that, there's one critical point that we have to decide, and that's the area threshold. So we have to decide at what area percentage of thermal comfort we count an hour the result as comfortable. When we have decided that, so in this case we started with a baseline scenario of 80% of the space. We can go on and make an assessment of each individual hour, again represented as dots in this case. So for the first day in this month, you can see that the morning hours are cool, and also are the evening hours. But then also we can do it for the whole month or even the whole year. And then what we usually focus on is the occupational hours, so between 8 a.m. in the morning and 6 p.m. in the evening. So in this example, what you would see is that roughly 31% of these hours are likely to be perceived as too hot, and 69% would be comfortable in this scenario. So what this means is that the STA 80, so 80%, in this case means that we have that the STA is 69%, sorry. And to summarize it, that means that in 69% of the time, more than 80% of the area are comfortable without heating and cooling. So that's in essence what we want to portray with spatial autonomy as a metric. So now the key question is, how can STA help us to design better buildings? And that's what we wanted to evaluate in a case study. So in this case study, we ran simulations for a typical office building in Sydney, Australia. So it's a kind of similar climate compared to this area just on the southern hemisphere. There we tested 3 zone sizes ranging from a single person office to a large open plan office. We tested 3 different design levels or passive design levels. So what we mean with that is that ranging from standard to advanced, the passive solutions integrated into these construction or design scenarios increased. And then also we looked into a current and future weather scenario. The goals here were to evaluate STA and its correlation with spatial thermal variability, so what I introduced earlier, but also how STA can help us to improve energy use and future resilience. So the first thing I want to address here is STA and the spatial temperature variability. So as I said earlier, the key advantage of having a spatially resolved metric is that we not only look into one point in the space, that's the average, we look into multiple points. And to advertise and to highlight why this is important, I want to show a few box plots. So what you see here is a box plot for the medium zone size and a standard construction. So what you see here is a range of the hourly temperature differences across the whole year and a distribution of that. And what we can see is that we have temperature differences ranging from going up to 7 degrees Celsius or 11 degrees Fahrenheit, which is quite significant. If we would just look into the zone mean for these particular hours, we wouldn't see any differences because we have only one point. And this is quite critical. So then if we look into other constructions, we can also see the impact of a slightly improved construction here. But then especially when we look into advanced passive design solutions and a high STA of, in this case, 79%, we can see that we can drastically reduce the temperature variability of the space. And that makes us aware of the heterogeneity going on. And this can be quite important for design decisions. If we then look into the large zones, it's kind of a similar picture. And in smaller zones, we have a similar trend, just that the temperature extremes and the variation is not as high. So what does it tell us? In this case, it tells us that there are significant hourly deviations that we wouldn't see if we just look into the zone mean. So spatial simulation and assessment of comfort is important. And also what we can see that the variability is more pronounced for larger spaces and in cases with a lower STA. So then, because I'm talking about spatial, the spatial dimension, I also want to briefly show some spatial, or the way how we can visualize it. So again, we have the three construction scenarios, so standard, medium, and advanced. And what we show here is for each of these points that we are investigating the annual temperature variability. So the difference between a maximum temperature and a minimum temperature for that particular point. So what you can see here is that for a construction, standard construction, closer to the windows, we have a very high temperature variability. If we slightly improve it, the variability goes down a little bit, but we still have the spatial variability that's quite significant. But if we then go to the advanced construction, and also to an example with a very high STA, we see that this variability is significantly reduced. So another way how STA can help us design buildings with lower variability, or at least we can have more control over it. We also looked into the future scenario, pretty similar image. In this case, the temperature extremes are just a little bit higher. The next thing we wanted to look into was STA and energy use and resilience, a pretty important topic. If you've watched Harry's presentation today, very relevant right now. So I want you to look first to the bottom of the chart, where again we have the STA values, so spatial thermal autonomy. And what we can see quite clearly is that with an increased spatial thermal autonomy, the expected energy use can be reduced significantly for a current weather scenario, but also for a future weather scenario. Then we also wanted to look into a proxy for thermal resilience. So in this case, what we decided to use was the operative temperature distribution across the whole year. And here again, we are comparing the different construction scenarios with their individual STAs. And here, this is also pretty significant. We can see that if we base our design on spatial thermal autonomy, we can actually, first of all, reduce the range of extreme temperatures that we have, and also the extreme values in this case. So what this means is that if we use STA to guide our design decisions, that will promote energy efficiency and also improve the long-term thermal autonomy of our building, which is great. So now the final question, compared to all the other metrics that we already use right now, what is the additional value of using STA? So what's the main benefit? So I want to conclude with this. Using STA in building design can lead to a better representation of comfort, so we know much more about the thermal differences across a space. It will naturally lead to promotion of passive design solutions that will improve thermal resilience of buildings. And this is the one that I'm actually most excited about, because we're talking so much about PCS. If we now have a better idea of thermal variability across the space, it will be much easier for us to plan for the integration of PCS and potentially mitigate local discomfort. Thank you very much. So this work is still under review for a conference that I'm going to present it in a few weeks, but I've stored everything on GitHub. So if you're interested to learn more about the paper, there's a PDF, but there's also the code that we use for the analysis. And please also join me for the breakout session together with Carlos later on. Thank you very much.